So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be going over triplet neural networks. Now, triplet neural nets are not a special kind of neural network, but rather a special kind of way to train neural networks. They don't require special or exotic architectures, and they allow you to do one simple thing. How do you take complex data and project it onto a feature space so you can identify similarity between different data points in that space? Now, triplet neural networks can be used for all sorts of things, and let me give you a few quick examples, and then we'll get into exactly what we're going to do today. Now, think about this. Let's just say you're trying to build an application for facial recognition. Now, traditionally, what you might do and what you might have seen on this channel before would be something like this. You would have your neural network, or let's just say you have your convolutional neural network to be specific, right? So you've got your convolutional neural network. Now, this convolutional neural network is feeding into a multi-layer perceptron neural network. And so you're feeding into what would be called in Keras terminology some dense layers. Now, at the end, finally, let's just say we've got 3 dense layers over here. These represent our dense layers. Now, the very last one would be the number of classes that you have, and you would traditionally do something like a softmax activation. So in order to train your facial recognition neural network, you would feed a face, like so, into your convolutional neural network. You would train it to classify that face into one of a few categories. And then after that, what you would do in order to classify new faces is you would just discard this layer altogether, and you would use the penultimate layer, you would use the second last layer, and you would use that as a feature vector. And that feature vector would then describe exactly what that face looks like. If 2 separate faces fed into this neural network have similar enough vectors, then you consider that they are the same face because the neural network extracted similar features. The noise may have been different, but the signal, the facial features that the neural network learned, they were essentially the same. But here's the problem. In order to train a neural network like this, first of all, you're wasting compute. And that's because you've got this entire last layer that's just doing classification that's going to be removed anyway. And plus, just because this neural network has great accuracy when you're training it on a certain set of faces, doesn't mean it's necessarily going to generalize well to other cases as well that weren't already in the training data set. So, a bias problem. Now, triplet neural networks can help you solve this. However, there are also other ways to solve the problem. For example, you've got Siamese neural networks. Now, Siamese neural networks, these are really fascinating. What you can do is you can essentially take your multi-layer perceptron neural network, and instead of having multiple layers, well, you would still have multiple layers, but instead of having a classification as your output, you would just have some kind of feature vector. And then you would have the same model over again, so you have the same convolutional neural network, the same multi-layer perceptron neural network, all right? Now remember, these are sharing weights. So these over here, these share weights. These over here, they share the same set of weights. They're the same neural network. But then you would feed in face number 1 and, of course, face number 2 into the neural networks. Now you have 2 separate feature vectors, because remember, there are 2 layers. At the end, you have feature vectors. And then what you do is you concatenate these, you merge them, all right? And after merging, what you do is you feed into another, say, multi-layer perceptron neural network. And this multi-layer perceptron neural network will then go ahead and predict one thing. It won't try and classify the face. It'll try to do a regression problem instead. Try and predict, are these the same face or not? And what this enables us to do is say, if these 2 vectors are very similar, then that means that this neural network is going to classify as well as the same face because you have similar vectors. In essence, these layers are going to learn to create feature vectors for the faces that you feed in. Or you could even use the entire Siamese neural network inside of your actual inference operation, although this can sometimes be a little bit complex because then you've got to run the whole neural network or at least store these vectors for every new input, and you've got to match every single input you already have against the new inputs. Sometimes it can be a little bit annoying to use this method, but it works. And this is where triplet neural networks come in. What if you don't want to have two separate inputs and then a place where you merge those outputs and then regress a value? What if you just want to have a single neural network, you want to have a single set of inputs, and that single set of inputs will then provide you with a single set of embeddings, and these embeddings describe the features that the neural network found. Enter triplet neural network training. Now, the way triplet neural network training works is quite interesting. The idea is that you only have a single neural network model, but this single neural network model is going to be able to create feature vectors for any input that you provide it. Now, the way this works is based off of some labeled data that you provide the neural network. What kind of labeled data? Well, let's find out. And in doing so, you'll also figure out why we call them triplet neural networks. So let's just draw this vertically this time. So let's say you've got a convolutional neural network again, right? Classic, simple. Now, what you have is a multi-layer perceptron network, of course, right after your convolutional neural net. Now, this is going to be considered your network, all right? And it's going to output some kind of feature vector. So no classifications here, just a feature vector. It could be, say, 100 dimensions. Doesn't matter. Depends on what works best for your specific use case. Now, what's going to happen is you're going to take some face, or actually, you're going to take three faces. You're going to take face 1, face 2, and face 3. But they don't have numbers. Rather, they have letters. You have face A, P, and N. Anchor, positive, and negative. Now, you can probably start to see where this is going. What you do is you feed all three of these inputs to the neural network. Now, you're going to have three separate outputs from your neural network. All of them are going to have the same shape. Remember, these neural networks, these three inputs don't correlate with each other. They're run through the network separately. Now, of course, you have your anchor embedding, your positive embedding, and your negative embedding. Now, what do you want to do? Well, the idea behind this neural network is that the anchor and positive that you feed in are similar images, and anchor and negative are dissimilar images. So for example, let's just try and create like an MNIST analogy. What you could do is you could feed in 0 and 0 into A and P, and then some other number like 8 into negative. Now you have an embedding for the number 0, another embedding for a different number 0, and an embedding for the number 8. Now here's what you can do in your loss function. Instead of having some kind of expected output like a classification or are these two numbers in the same class, instead what you can do is you can try and maximize the distance between anchor and negative, but minimize the distance between anchor and positive. And when you do this, the neural network, guess what? The final layer is going to learn a feature embedding that describes the input that you provide it, such that similar inputs have similar output vectors. And by doing so, you can, for example, cluster inputs. And that's exactly what we're going to do today. So, in Keras, we're going to take a regular neural network and wrap it with a super simple function that enables the model to take three inputs, and we're going to create a custom loss function in Keras using a special little workaround that will actually take this anchor, positive, and negative input, and it'll calculate triplet loss. As a matter of fact, we're not just going to be using any triplet loss, we're going to be using a special kind of triplet loss developed by IBM Research while they were working on Project Debater. Now, how exactly it works, why it works, that's a topic for an entirely separate video. But we're going to be using some cutting-edge loss functions in this tutorial. As a matter of fact, Keras doesn't particularly support loss functions like this because Keras expects that, hey, you have your model output, you have your expected output. But in this case, we don't really expect anything because we don't care. We don't care what the vectors are. We just care that anchor and positive are closer and anchor and negative are further away. That's it. And so that's why we're going to be using a little bit of a workaround to have an empty expected output, and then the loss function knows what to do with the three separate outputs that we provide it with. And so now, without any further ado, how about we take a look at taking MNIST data, creating feature vectors for it with a triplet neural network, and then running it through a library called UMAP for dimensionality reduction to bring it down to just 2 dimensions, and then plot that out using Matplotlib to see if we can see 10 different clusters of digits. So, without any further ado, let's get into it. Alright, so what I've got open right now is a Jupyter notebook on Skills Network Labs. Now this is of course a Python notebook, as we're going to be using the Keras library. Particularly, we're going to be using tf.keras, tensorflow.keras, which is the TensorFlow implementation of the Keras API spec. Sometimes it can be confusing as to what that means, but it's Keras. Now, Skills Network Labs is available for everybody to use. It's this free environment where you can start up your own notebooks and train neural networks and try out different things. You have different notebook kernels, like for example Python, Swift, Julia, and a lot more. There will be a link to it down in the description below, as well as to a GitHub gist with this notebook, so you can download it, upload it to Skills Network Labs, and train it for yourself, or train it on Google Collaboratory, or even your own environment if you have access to one. So let's begin. Now to start off, we've got a little command line command, which is just pip install TensorFlow version 2, and another package called UMAP learn. Now, UMAP learn is a package that implements UMAP, which is a dimensionality reduction package. Now, how exactly this package works, we can get into that in the future. For now, all you need to care about is that it's kind of like, it achieves the same sort of fundamental goal as another algorithm like PCA or TSNE. So the idea is, how can you go from, say, 100 dimensions to just 2 dimensions so our mere mortal minds can actually visualize it? Now, of course, humans can't visualize more than 3 dimensions because we live in a universe with only 3. So if we've got 100 dimensions in our feature space, there's no way to visualize it. However, if we were to actually use an algorithm like UMAP to bring that down to just 2 dimensions, then we can visualize it. Problem is that we end up losing some information in that dimensionality reduction, but don't worry about it, there's still enough to give us an idea of what it would be like projected into 100 dimensions. But I'll get into what that means and what that actually entails in just a moment. Alright, so as you can see, this command line command just ran, and we've installed our packages successfully. Now, I'm going to run this cell with a bunch of imports. Let's see if it works. Sometimes it'll actually crash at this cell, because after the pip install, you've got to restart the Jupyter kernel. Now, there we go, it didn't crash, that's great. So it actually installed, and we were able to import perfectly. So now let me just quickly give you a brief of what we imported. First of all, the random package built into Python for just selecting random elements from arrays. The Matplotlib package for plotting. NumPy for, of course, numerical operations on NumPy arrays. We've got UMAP for dimensionality reduction, and then a bunch of TensorFlow.Keras libraries. Now, we have to import the backend for this because we're going to be writing a custom loss function, and we need to run operations on Keras tensors. And the backend is going to allow us to actually get those operation functions where the gradients are actually defined. Then we also need the MNIST dataset, luckily built right into Keras, so you don't need to download or do any of that weird stuff. Also, we're going to import model from tf.keras.models, so we're going to be using the functional sort of way of building a model in Keras, and then just import all the layers. This is not best practice, but instead of importing every layer one by one, I thought we would just do import star. So now, after this cell, pretty simple, self-explanatory, you didn't come to this video to see this. It's just taking the MNIST data set, loading that data, putting into the XTrain, YTrain, XTest, and YTest arrays, reshaping them so they actually fit the neural net. So there's 60,000 elements in training, 10,000 in testing, with only a single color channel and a 28 by 28 image. And of course, we want these pixel values on a scale of 0 to 1 instead of 0 to 255, as you would get with an 8-bit unsigned integer, and so therefore we just divide by 255 and convert to a 32-bit floating point number. Now, in terms of the actual classes, there's only 10 categories with MNIST, of course. There's just 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0. And so those are the 10 classes that we have for our data. Now, next up is something that, again, is not necessarily best practice, but works for triplet neural networks. What I've done is I've created a generator function. And this generator function in Python is essentially going to be something that you can continuously call from an iterator. And what it'll do is it'll continuously gather random triplets from the data set and put them in a way so that you can train your neural network. So let me actually walk you through this. So what happens is this data generator gets a batch size. By default, it's going to be 64. And then it has an infinite loop, and in every iteration of the infinite loop, we create 3 lists: the anchors list, positives list, and negatives list. Now, these 3 separate lists will contain all the samples that will be trained in a certain batch of training. And so every single time this function yields, it'll be returning these lists, and there will be 64 elements in each of these lists because the batch size is 64 by default. Then there's just a simple for loop where we iterate the number of batch size times, so in this case 64 times, and then I do one thing first. What is going to be my positive class and what is going to be my negative class? For my positive class, I will extract an anchor and a positive sample. For my negative class, I will extract a negative sample. And the way I'm going to do that is by using random.sample and random.choice. So what I do is I take the xtrain numpy array and I say, okay, give me only the samples inside of this array where you know that the class of that sample is equal to the positive sample class. And so as you can see over here, we have a list with 2 different classes. One of them is our positive, one of them is our negative. And over here I'm saying, okay, only give me the images of digits if you know that they are in the positive class. And then out of all of those, which there should be around 5,000-ish, select 2. Random. Select 2 separate elements. So one will be our anchor, one will be our positive. Then we just take the same xtrain array, numpy array, and then choose all of the samples where you know that the image is from the negative class, and then choose just one random image from that negative class. Then all you got to do is take the anchor, positive, and negative, put them inside the list, and then after the for loop, you've built your batch. Now what you're going to do is you're going to yield 2 things. Remember, you should be yielding, according to the Keras spec, a tuple. And the tuple should have 2 values, of course. The first one should be a list with the 3 separate inputs to the neural network. One is the anchor, second one is positive, third one is negative. So 3 separate inputs in a list, like so. Now, the next one should usually be the expected output from the model, but in this case we don't expect any output, so we're just going to do zeros with a batch size of with the shape of batch size 1, and the type should be float32. And so just like that, we've got our data yielded and our data generator is finished. Now, after the data generator, then we got the triplet loss function. Now, this is where the interesting part comes in. Now, remember, in this case, our neural network is going to have 100 features that it outputs. And so what the triplet loss function is going to do is it's going to receive a tensor with shape none 300. And that's because we are concatenating none 100 3 times. So we are concatenating anchor, positive, negative into one output just to satisfy Keras and tell it, okay, we only have one output because it only supports that one output. And then once they're merged into this, then the triplet loss function will slice them all out into separate tensors again, and then we're going to process on those sliced tensors. So we take the anchor slice, the positive slice, and the negative slice in that order. And this is where the special loss function actually comes in. So the way this works is that we get the L1 distance between anchor and positive and anchor and negative. So this is the L1 distance between anchor and positive. And then we also have the L1 distance between anchor and negative. All right, so that's pretty simple stuff. You've got your distances. Now, this is where the sort of weird part comes in. What you're going to do is you're actually going to take pos dist and negative distance, and you're going to put them into an array, and you're going to calculate softmax on that array. Now, why are you doing this exactly? It's because you want to get a probability of either the positive or the negative being closer to the anchor. Now, after that, what you want to do is you want to somehow tell the loss function that your objective is to increase the probability of positive and decrease the probability of negative. And so the way you're going to do that is by using this little function developed by IBM Research. So you're going to take the absolute value of the positive probability and add it to the absolute value of 1 minus the negative probability. Now remember, you're doing this across batches. So the axis over here is going to be across batches because you don't want batches to interfere with each other's learning. So you're going to do it across the batch, and then you're going to mean the loss values for each individual training sample within that batch. And that's why we've got k.mean here. And there we go. That's the loss function. Simple as that. Now, this loss function is surprisingly very good at what it does. And so we're going to take a look at that in 1 second, but let's go ahead and take a quick break to actually run these 3 cells. As you can tell, we've been able to download the data and actually run these 2 functions, so they are valid. Next up, we are going to create a super simple, most certainly not optimized, but working MNIST classification model. So if I go ahead and run this, we've got a super simple MNIST convolutional neural network model with 190,148 total parameters. And this is going to give us a dense output with just 100 features. Now, all of the activations in this network are rectified linear units. Next up, super simple wrapper around that model that enables it to become a triplet neural network. So over here, we have 3 separate inputs, the anchor, positive, and negative inputs. Then we have an output layer. The output is just concatenating the model output for each input together into that same none 300 we were talking about, and then constructs the model and prints out a summary. So if we actually go ahead and run that, as you can see, give that just a moment to process. Sometimes it takes a moment because Keras is slow in this case. Give that a second, the cell will run, and in theory we should have 3 input layers, which are, as you can see, 3 input layers which are connected to that model. And remember, this is just one model, not 3 separate models. One model that will output 3 separate vectors that are then concatenated into one, and then this one is fed into the loss function. Now, finally, all we need to do is compile the triplet model. As you can see, it worked. We pass it our custom loss function, and Keras is actually quite intelligent. It'll actually go through that loss function with a dummy tensor to make sure that everything works, and it verified. The fact that the cell actually executed means it went through the function with a dummy tensor, and it worked. And then we've just got an atom optimizer, super simple optimizer, not a simple optimizer, but a great optimizer. My favorite, the one that I use by default in a lot of cases. And finally, we've got the fit generator function. The fit generator function is going to take the data generator that we had just built a little while ago, the number of steps it should run per epoch, in which case I've done around 150 because 150 times 64, we're going to cover around 10,000 images per epoch, and then just 3 epochs. Now, we could certainly do a lot better. We could go through the whole data set in every training epoch, which is technically what we should be doing anyway. We could do more epochs. We could have a better model architecture. But in this case, I wanted to tell you how triplet neural networks work, and I don't want to tell you how to optimize a neural network training specifically for MNIST. So we're not going to do that right now, but we're going to run the fit generator function, and currently this notebook is not powered by GPUs. So the training could take a couple of minutes. As you can see, the loss function is going down quite rapidly. We're currently at around 0.68, 0.65, 0.62. These are big steps down we're taking. And that's a good thing. The lower our loss value, the closer the neural network is to learning exactly what it is that we want it to learn. And so let's go ahead and speed up this clip so you don't need to watch paint dry. And in just a few moments, we'll take a look at our neural network after it's done training, see what the loss value is, and see if we can actually visualize the clusters that the neural network learns to create. Okay, so there we go. The triplet model is now done training. As you can see, we get the callback history. That doesn't matter. That's just the return value of fit generator. Now I'm just going to save the model in case. So if something else crashes the kernel, we don't lose the saved model because it has happened before and it has wasted many hours of training time. So let's make sure we save before we do anything else. Now, what I'm going to do is I'm going to take the test data that has never been fed into the model, for training at least, and I'm going to feed it into the model. Remember, now that we're no longer training, we don't need the triplet shell, and we can just use the model as a regular old model that takes a single input and gives us a vector. And the way I do that is by treating the model as the third, or actually fourth, layer within the triplet model, because if you take a look, 0, 1, 2, 3, inside the triplet model, our actual model is technically a layer within it. And so I get that model, and then I predict on the X-test dataset. And what that does is it gives me embeddings for every image inside of the testing dataset. So if I go ahead and run that in just a few seconds, we should get an array of shape 10,100. There we go, 10,100. So 10,000 samples, 100 dimensions for each embedding. Now, again, we can't visualize 100 dimensions. So I'm going to run a little thing called UMAP, and what UMAP is going to do is it's going to take the 10,100 and convert it to an array of size 10,002, so dimensionality reduction. Now, the specific parameters I'm using that I found come up with a pretty good visualization. Number of neighbors 15, and minimum distance is going to be 0.3. The metric for calculation is going to be correlation. Again, I'm not going to go over how UMAP works today. That's going to be a topic for a separate future video. All you need to know is that it's an amazing dimensionality reduction package. Now, I've told it to fit its internal model on the embeddings that we got from the testing data, and also transform them and run that dimensionality reduction. And then, of course, print out the shape, and after this cell executes, we're going to go ahead and print out a scatter plot and see if it actually, well, worked. This is just a warning. You don't need to worry about this. There we go. We're already done. That was really fast. And now, without any further ado, here's what we're going to do. We're going to create a scatter plot where each dot represents the dimension, the embedding for one of the input images. Now, every single sample will have a color that represents its class. So the idea is that if the model learned things correctly, then dots with the same color will be grouped closer together, and there will be visible clusters of colors, each color representing a different number in the MNIST dataset. So if I go ahead and run, let's see if it works. Oh, it actually seemed to have worked. Let's take a look at this, shall we? So now, as you can tell, we have a couple of different clusters. We've got this purple over here, we've got these green clusters, we've got this yellow cluster, a sort of bluish color, another bluish color. Now, there's one thing I want you to do first. Let's go ahead and count the number of clusters. So we've got 1 cluster, 2, 3, 4, 5, 6, 7, 8, 9, and 10. How many classes do we have? We have 10 classes. So as you can tell, we were able to get 10 clusters representing the 10 different classes that we have. Now, there is something else to keep in mind. As you can tell, it's not a very neat clustering. As you can tell, there's a little bit of green in the purple over here. There's more green in the purple here. There's some yellow in the green. There's some there's colors overlapping with other colors. Now, there's a few reasons as to why this is. First of all, we didn't train a very good model because it wasn't optimized. Second, remember, when we went from 100 dimensions down to just 2, we lost a lot of information. Something that could be very easily separable in 100 dimensions could be not separable at all in 2 dimensions, or at least not obviously. I mean, even in a state like this one, even with just 2 dimensions, if you were to use the UMapped data, you would still be able to create a pretty good classifier, because, I mean, I could literally just draw a couple of lines and we would have, or a couple of curves, and we would have separated the classes. But the thing is, in 100 dimensions, the network would have so much more information to go off of that it may as well be separable. Now, we might even be able to solve this problem by going from 2 to 3 dimensions and see how it's even more separable. But for now, what matters is that we saw a neural network given no labels, only the fact that, hey, these two are similar, this one is not similar to the anchor. Based off of just that information and using a custom loss function, we were able to create a network that took any arbitrary image of a digit from 0 to 9 and was able to convert to a vector that describes what that digit is. For example, this could theoretically be the 0 cluster, this could be the 1 cluster, this could be the 2 cluster. Doesn't really matter. What matters is that we were able to separate different digits into different clusters. If it works in 2 dimensions, it's got to be better in 100. And so that is how triplet neural networks work. Now, there's a lot more you can do with this than just classifying data that already has classes. Now, MNIST, of course, is meant to be done as a classification problem. It would be better to do this as a classification problem. But what I wanted to show you is that the model was capable of creating such absolutely incredible vectors like this one. And so now, what I'm going to do is I'm going to give you this notebook down in the description below, and if you'd like to go ahead and modify this notebook and use this loss function for your own neural networks and your own practical use cases, feel free to go ahead and do so. And so thank you very much, everyone, for joining in today. I do hope you enjoyed. If you did, please make sure to leave a like down below. Apart from that, I would absolutely love to answer any questions you may have or hear any feedback as well, so leave that down in the comment section below, or you can email it to me at tajimanny@gmail.com. And once again, thank you very much for joining in today. Goodbye.